Great, I think we can start. Welcome everyone for a new IGES seminar, and thank you a lot for joining once again. This week's speaker is Hilmar Gudmundsson. Hilmar is a professor at Northumbria University in Newcastle in the UK, and is conducting research in glaciology with a specific focus on the future evolution of glaciers and ice sheets in a warming world. And today he will be talking about the dynamics of large ice masses. So yeah, let's get started. And Hilmar, over to you.
Excellent. Yeah, thank you so much. So you can hear me and you can see me. It's all working.
Yeah.
Okay. Well, I first of all, I want to thank you guys for organizing this. I think this is wonderful. This is really fantastic to have this opportunity to present my work, and I definitely enjoyed very much some of the talks that have been sort of over the past, how long have you been doing this? 2 or 3 months by now? Or a whole year? How long have you been doing this? Everything merges together. But this has definitely been a highlight. I really enjoyed this. I haven't been to all of the talks, but many of them I definitely have enjoyed. So I thought I would go through a few things which relate to dynamics of large ice masses. And some of those things you will know. They won't be new. Some of the things hopefully will be somewhat new. I'll also present a few papers which came out earlier this year. But first of all, maybe I should present the group we have at Northumbria University. I'm very fortunate to have all these people that I can talk to and discuss things with. Emily Hill, Jim Jordan, Adrian Jenkins, Camilla Shelbe, Johan Barnes, Christopher Bowl, Sebastian Rosia, Christina Gerli, Mahdi Mohammed, Tom Mitchum, Jan Derit, Marina Hasselhoff, Ronja Rees, and Zainab Sun, who will be joining us later this year, with Ronja and Zainab. So let's start with something simple. So why don't you guys solve these equations for me? You're all very clever. This will not take you a minute. So we have this problem here. It's a mountain sitting, a glacier sitting on a mountain. The blue color, that's the glacier. And the red line, that's the ELA, equilibrium line altitude. And on the right-hand side, we have the surface mass balance distribution, which is here a function of horizontal distance. And we have the equations that we like to solve, maybe unnecessarily complete. I have the acceleration term in here, but that's okay. And we have the definition of the geometry, which is sort of a linear drop in elevation, and the surface mass balance, which is a linear function of horizontal distance away from the top of the mountain. And you can use values like n equal to 3 and a, whatever you want to use. And the mass balance at the top of the mountain is 5 meters a year and then decays with distance. A1 times the absolute value of x, where A1 is 1 divided by 5,000. So this is a problem that you would expect maybe people who are interested in glacial mechanics to be able to solve. And the question is this a simple problem, or is this a complicated problem? And while you sort of ponder what the answer is, I'm going to use a numerical approach to solve this problem. So we are doing this right now. It's running, you can recognize these MATLAB figures. So on the right-hand side, you see the mountain, and you see the glacier forming on the top of the mountain. You see the ELA, and with time, we're piling snow on top of the mountain, according to this function here. With time, the glacier thickens, and eventually it starts to flow down the slope of the mountain. Over here to the left, topmost panel, you can see both the glacier length, which is on the left-hand side, and the mean specific mass balance, which is on the right-hand side. That's the red dots. And you can see now how the length, that's the blue circles, are increasing with time. You can also see here on the right-hand side that the glacier is clearly snout of the glacier is clearly moving downhill. You can see on the left-hand side here, the lower panel, the ice thickness distribution, greatest ice thickness around the Ela approximately. And here you see DHDT, most of the elevation change is happening at the snout as it advances. So are there any guesses as to what the steady state length of this glacier will be? And are there any views on whether this problem is easy or complicated? Easy means you can sort of figure this out based on some general principles. Complicated means here you actually have to sit down and solve the equations. You will have to solve the equations on the left-hand side or some similar equations to come up with an answer. So I don't know if you guys have a chat function. You should have that somewhere. Maybe someone wants to guess. You're sort of running out of time. The model is approaching steady state slowly. And I think you can see it is approaching a length of, what is it? 50 kilometers. And you see that DHDT is approaching 0. And there we are. I ran this for 500 years. So the thing is, this is a simple problem. In the sense that we don't really have to solve the equations. I did solve them here, but if we are only interested in the steady state length of the glacier, we can use mass balance arguments to estimate or calculate how long the glacier has to be. So I used a linear mass balance profile, 5 meters here at the top, and then it changed linearly with horizontal distance at this rate, 1 divided by 5,000. So if it is +5 for x equal to 0, the integral over the mass balance curve will become 0 once that mass balance, the specific mass balance, reaches the value -5. So it goes from +5 linearly down to -5, and then the positive part of that integral is equal to the negative part of that integral. So we wanted to be it will be 8 times x equal to 10, so it will be 10 times 5,000, so it will be 50 kilometers. So you can see that directly from this number here, that the length, the steady state length will be 50 kilometers. So this is sort of a key thing for me. And when I was learning about glaciers, I guess the reason I'm showing this to you is that I went through a bit of a process myself. I was sort of fascinated by the equations, and I thought, you know, that's what we need to do, and often that's exactly what we need to do. But sometimes very simple arguments give us the answer, and we can also see from simple arguments such as this one that the answer will not depend on various details that enter this problem. One might think that this would depend on the value of the rate factor A. Well, it doesn't. The transient evolution towards a steady state does, but not the steady state value itself. Now, you will possibly be screaming at me and saying, well, that's all because you're ignoring the surface elevation mass balance feedback. And that's absolutely true. I'm not including that here, but we have limiting situations where the surface elevation mass balance feedback can be ignored. And in that case, to calculate the steady state length of glaciers is actually quite simple. There are many situations where this is a very good approximation. And it's important to realize, and this was a process that I went through, that actually glacier mechanics, at least when we're talking about alpine glaciers and maybe ice sheets such as the Greenland ice sheet, the ice dynamics only become really important because of this surface elevation mass balance feedback. So what we really need to get right is the surface elevation. I'll show you another example, which is sort of the other sort of extreme. This is a solution by Wertmann. You may have seen this. This tends to be something that people teach in sort of introductory courses to glacier mechanics. But let's let's look at this. Let's just see this as another extreme limit where everything is about the surface elevation mass balance feedback. So this solution by Wörthmann is shown here. The curve, the blue curve, is actually the surface elevation of an ice cap or an ice sheet. And this is an analytical solution. You arrive at this by using the shallow ice approximation. And you specify a somewhat constructed function of constructed surface mass balance function as a function of elevation, in the sense that above a certain value, 2000 meters in this particular case, the surface mass balance is positive and constant. And below that elevation, the surface mass balance is also constant, but has a different value, a negative value. So this will be an ablation area, and across that ablation area, the mass balance has a constant value, negative value. And over here, we have the, let me see if I can get the pointer going again. Over here, we have the accumulation area where the mass balance is equal to A plus. And this problem has a solution. That's actually quite interesting. You can solve this and you get an equation for the length of the glacier, which only depends on the ratio between A plus and A minus, and the height of the ELA, and this factor C, which includes the rate factor and the ice density and so on. So let's look at the properties of the solution. This is a steady state solution. Now we can also solve this numerically. We can put an ice sheet or set up an ice sheet so that it is exactly this solution. We start with this solution and we perturb this solution in some fashion. So here I have the surface elevation, and ELA is over there at 2000 meters as before. And down here on the left-hand side, I have introduced a small perturbation in the surface mass balance. So A plus is equal to 1, except that I just changed it to 2 for a few years and then took it back to 1. So this is like a tiny nudge to the system, a small perturbation to the system. Now, if this system was stable, we knew that this was in steady state, but if it's stable, then we would expect that once we take this perturbation back, the system would approach its previous steady state. But as you will have seen, the snout of that ice sheet is advancing. And down here on the right-hand side, you see that the volume is increasing. So it does not look as if this solution was to go back to where it started. If it were trying to do that, then this red line, which is to be growing away from the original value, would be going down rather than up as it is doing. So this was something that Wörthmann pointed out. You can create an ice sheet, basically in any climate. If you have a flat surface and you have a climate which just changes in such a way that below a certain elevation, the mass balance is negative. Above that elevation, the mass balance is positive, constant in both cases, but different values. You can create a steady state ice sheet, but this steady state ice sheet will be unstable. And that's what we're seeing here. We're seeing this unstable behavior. This is all about this feedback between the elevation and the mass balance. That's what's going on here. So this would be, I would say this is a complicated problem, surprising problem. Also, if you look at the solution for the length of the glacier or the ice sheet, and you imagine that you increase the snow accumulation, A plus, then the length of the glacier will become smaller. So again, this is something which is surprising, but the math shows you that this is the case, and it shows the importance of looking at limiting cases such as these. So we can see that if we have horizontal variation in surface mass balance, there's no surface elevation mass balance feedback, then glacier dynamics becomes pretty much irrelevant, at least if we're looking at the steady state solution. Soon as we introduce surface elevation mass balance feedback, on the other hand, the situation becomes really, really interesting. A lot of cool things that are happening, surprising things that are happening. So let me move a little bit ahead. You may have seen this figure many times before. I actually don't know where I got it from originally, but it shows the difference, the key differences between the Greenland ice sheet and the Antarctic ice sheet. In Greenland, more or less, we have this division between an area where the mass balance is positive, accumulation area, and where it's negative. Over Antarctica, on the other side, the surface mass balance is basically always positive. Everything is an accumulation area, just about. And in Greenland, the ice sheet reaches the ocean. We have tidewater glaciers, but we don't have the formation of significant ice shelves. There are a few ice shelves around Greenland, but not many. Whereas around Antarctica, we have these huge, huge ice shelves. And finally, most of Greenland, not all of it, but most of it is situated on bedrock above sea level, whereas large part of Antarctica are below sea level. So these are sort of the key differences. And this very early on suggested that the dynamics of these large ice masses, Greenland and the Antarctic, would be very, very different. And this concept came up about the stability of marine type ice sheets. So this is, again, a numerical simulation. Here we're looking at a marine type ice sheet. It sits on bedrock, which is black. It is in contact with the ocean, which is dark blue, and the ice itself is light blue. Now, this is the MISMIP intercomparison modeling experiment 3A, and many groups, modeling groups around the world participated in this experiment, and this was a quite significant event for our community. Before this intercomparison experiment was conducted, there was a lot of confusion about the stability regime of marine type ice sheets. There might even still be some, but after this experiment, and also due to the paper by Christian Schuf, the situation became much easier to understand, and that we sort of started to have a general consensus. So when we have unbuttressed ice sheets, marine type ice sheets, the grounding lines over retrograde slopes are unstable. We can have steady state solutions, but they will be unstable. Now, what is going on here? Actually, if you think about our first example, where we had a horizontal variation in surface mass balance, the basic argument is maybe not that different. So let's break this down a little bit. So we have 4 lines here, or 4 curves. Let's first start with the black one. That is a that's the bedrock. It's a bedrock profile. Over here, it's above sea level. Sea level is at 0, and then it sort of dips down, goes below sea level, negative values, goes up again and down again. So this would be a section of prograde slope. This would be a section of retrograde slope, then again a prograde slope. And then let's look at this line here, the dashed line. This is the flotation profile. So whenever we go below sea level, or the bedrock goes below sea level, we can think about the minimum ice thickness that an ice sheet must have for it to be grounded. And that gives us the flotation profile. And that is pretty much the inverse of the bedrock profile, with some density ratios being multiplied. So these are the 2 lines, the bedrock profile and the flotation profile. Now the other 2 lines they represent flux, and the units for those 2 lines are actually on the right-hand side. So first of all, we have this, I think this is called magenta line, I think it is, straight line, which represents the surface mass balance flux. So it's simply the integrated surface mass balance above a given location. So it starts with being 0, and then, so that's the y-axis that you should be looking at. Starts with the flux being 0, and then with distance, if the surface accumulation is a constant, then it just increases linearly with distance. So this integral the surface mass balance above a given location. So this is the surface mass balance flux. And if we want to have, just like before, a steady state solution, then that must be where the integrated values of all fluxes, surface fluxes and discharge and so on, add up and are equal. Now, the red line is the flux across the grounding line based on an equation that we mentioned in a little while. And we can see immediately that only when these two flux curves cross each other can we have a balance between what's coming in and what's coming out. And the grounding line will only be stable if, when we increase the grounding line position a little bit or shift a little bit downstream, the grounding line flux, or the ice dynamical flux, grows faster than the surface mass balance flux. If that happens, then the ice sheet will also realize, wait a minute, I'm a little bit too small now. It will retreat and go back to where it was before. So this is the condition that we have. And since we know what the ice thickness will be at the grounding line, because that's given by the flotation profile, we can sort of work our way through this. And we conclude that if dq dx is to be, let's say, positive, let's just look at the signs, then dq dh will have to have either the same or the opposite signs of db dx. And since we see that it's a minus in front of here, if we want this to be positive, then if db dx is positive, then we see that dq dh must also be positive. So if db dx is negative, then this becomes positive, and for this to remain positive, dq dh has to be positive. So whenever db dx is negative, dq dh must be positive, and that's a condition for the stability of the grounding line, which is just based on sort of mass considerations. Now there's a sort of an implicit assumption in here that you can actually write down an equation for Q as a function of H, but that can be done. So all grounding lines on retrograde slope, this argument would suggest, are unstable, and all grounding lines on prograde slope must be stable. But it turns out the situation isn't quite this simple. So this is another intercomparison experiment based on a paper that I think I wrote somewhat earlier, which showed that you can actually get stable grounding lines on retrograde slopes, which goes directly against what I just said on the last slide. And to understand this, we need to understand the concept of ice shelf buttressing. So ice shelves can provide a sort of a back force to the grounding lines. So if we have an ice shelf such as this one here, and it has some contact with the along its sides, along its margins, then that will restrict the ice flow. And if we then change the thickness of the ice shelf, then that back force or buttressing force will also change. So we have now a mechanism whereby we can affect the flux across the grounding line by either increasing or reducing the buttressing provided by the ice shelves. The whole thing is sort of not particularly complicated, but sort of interesting. You can have a perturbation in the strain rates along the grounding line. And the question then becomes, how large is that perturbation and how far upstream does it propagate? And the perturbation, the velocity you get after the grounding line will then be integral over the perturbation in these horizontal strain rates from over the distance upstream of the grounding line. So the effect will depend both on what happens downstream of the grounding line, how much thinning we have over the ice shelves, but also on the mechanical conditions along the bed upstream of the grounding line. So, for example, if the bed upstream of the grounding line is very slippery, then this perturbation will be felt much further upstream, the perturbation in strain rates, and we can expect the perturbation in velocities to be larger. So this is an effect which is easy to understand, but difficult to quantify in a particular situation. Let's go back to that NISMIP experiment we saw before and look at this in a map plane view. This is the video that I showed you before for the confined ice shelf. And you can see here the grounding line position as calculated numerically, and various models came up with almost exactly the same profile for the grounding line. And we can see that the grounding line sits here in a region of a retrograde slope. So between these two vertical lines here, the slopes are against ice flow, retrograde slopes. So if we didn't have something that stabilizes the situation, if we were here in the 1D flow line situation, this stable position at the retrograde region of the bed would be impossible. And so why do we have this? And it's maybe a little bit difficult to fully understand what is going on here, especially in a numerical model where it's difficult to get an insight into the physics. But broadly speaking, if you were to shift the grounding line, you would change the flux, not just because the ice thickness of the grounding line is changing, but also because the area of that confined ice shelf is changing, and the buttressing provided by the ice shelf is changing. So now I have these sort of two different processes that are going on. You could think about this as the explicit dependency of the flux on ice thickness, and then also the change in buttressing as the geometry of the ice shelf changes. And you can play games, you can change the width of that channel, and you see that depending on the width, the grounding line is either on a prograde slope, retrograde slope, or exactly right between. So the conclusion has to be, we cannot make any statements about the stability regime of grounding lines based on local slope. Simply cannot be done, except in the limiting case of an unconfined ice shelf, where the answer is quite simple. So again here, looking at the position of the grounding line as a function of the width of that channel, and between these two horizontal red lines, the grounding lines are located on a retrograde slope, and you can see that the position of the grounding line looks to be a very smooth, sort of not particularly interesting function of the width. So this sort of forbidden region is found there. These are all stable grounding line positions. We did perturbation analysis of this. This all looks just fine. So if there's any sort of single message you take home from my talk here today, then let that be this: the stability of grounding lines cannot be determined from local slope consideration. We know that by now. We know that we have known this for some time by now. So this is something that you can. I don't think this will change. I think we will learn much more about various limiting cases and much more about the processes, but I think it's clear now that we cannot make general statements about the stability regime of grounding lines just based on local slope, except in that particular case of unconfined ice shelves. Now, why is this happening? As I mentioned before, the grounding line will be unstable or stable depending on the sign of dq dx. So if you have positive surface mass balance and we shift the grounding line a little bit downstream, the integrated mass balance above the grounding line position will increase, and dq dx has to increase by even larger amount for the grounding line then to want to return to its previous location. And that gives us this condition dQdH positive for dBdX negative. Well, here we can see that due to buttressing, the relationship between flux and ice thickness can be reversed, so that instead of having an increase in ice flux with increase in ice thickness, we can have a decrease in ice flux with increasing ice thickness. So again, this is absolutely fascinating, and it's at least currently, with our current understanding, pretty much impossible to give any general statements about the grounding line of the Antarctic ice sheet without actually conducting specific numerical studies. Let me just continue with this a little bit, because it is appearing as if that 1D situation is a very, very different case from the sort of confined situation. So on the left-hand side, we have a well-known analytical solution for the geometry of an ice sheet, sorry, an ice shelf. And on the right-hand side, we have a numerical solution for the geometry of a confined ice shelf. So the ice shelf is over here. Here, the solution starts at the grounding line, x equal to 0. And you can see here the upper surface and the lower surface shown in blue. And you can see the ice velocity shown in red. Now, you can see that what is very noticeable is how quickly the ice thickness decreases with distance downstream from the grounding line. Now, I think it was Sam Perkla who pointed this out to me, that you can actually see the same thing sort of happening in the numerical solution, but now it's tiny. This is, if you look at the balances between different terms in the equations we're looking at, the balance which is giving us this reduction here, and actually goes all the way down, is only located or confined to this small area over there. As soon as we go a little bit further downstream, the profile of the ice shell is actually determined by lateral constraint. This is a profile you get because the lateral constraint of the ice shelf, and as soon as you get to the unconfined section of that ice shelf, it changes again. So this is a balance you have in the confined case, or can have in the confined case, but you can't have in the unconfined case. And just look at these two curves. Look at the profile on the left-hand side of this ice shelf and the profile of this ice shelf over there, and just ask yourself, well, how do ice shelves around Antarctica look like? Do we have this sharp reduction in ice thickness as soon as we cross the grounding line, or as we have here on the left-hand side, or is it more like what we have here on the right-hand side? And of course, the answer is it's much similar to what we have on the right-hand side. So how can we quantify buttressing? Well, I'm not going to go into too many details, but just say that we can quantify this through a number. It's the buttressing we have when the ice shelf is unconfined, or the value for the horizontal stresses we have, which is 0.5 times rho times g times h. This rho is actually rho times 1 minus rho divided by rho water. And then the value that we actually have in a given situation. Now, if we have an unconfined ice shelf, n becomes equal to 0.5 times rho times g times h, and theta is equal to 1. But in the more general case, n will be something different, and we will need to calculate what that is for a given situation. But if theta is approximately equal to 1, then we can sort of use this Flux formula by Christian Schuf and insert this theta in there, which I think Christian actually did towards the end of one of his papers. And this might be like an approximate expression for the flux across the grounding line when theta is approximately equal to 1. But is it? Now we looked at this, or rather Ronja Rees looked at this, and there is nothing that's stopping you from just calculating these things. If you have a numerical model you sort of trust in, there is nothing stopping you from calculating the stress tensor here and calculating theta. And it turns out, and I think this is profound, this is very, very interesting. It turns out that theta is far from being equal to 1. It's usually smaller than 0.4. It can even become negative. So what this is telling us is that the most grounding lines of the Antarctic ice sheet are highly buttressed in the sense that theta is quite different from unity. Now, this flux formula was not designed for any values far away from unity. And you can see that if theta becomes less than 0 and you raise a negative value to this exponent over here, you will generally find, except for some particular combinations of m and n, you will get a complex value for the flux, which should show everyone that the formula has broken down. Now, another interesting thing, and this is another paper, also with Ronja's first author, is that the buttressing is actually provided by very limited parts of the ice shelves. So here we're looking at sort of a map, a sensitivity map of ice flux across the grounding lines to thinning or perturbations in ice shelf thicknesses. So here we perturb, or Ronja perturbed ice thicknesses within a given square, and then calculated the impact that thinning or that perturbation had on the flux across the grounding lines. And the value that you then get, sort of normalized, is represented by these colors. So this is logarithmic, and if this is red or goes to black, it's much larger than when it's blue, yellow, or goes to white. So you can see that the red colors and the dark colors are really concentrated close to the grounding lines, and that large parts of the ice shelves are almost white on this color scale here. And again, remember, this is logarithmic. So this is telling us that most of the buttressing, and the buttressing is really key for the dynamics of the grounding lines, but most of the buttressing is provided by small parts of the ice shelves, and the remaining parts are mostly passive. What follows is then, and this is not really that surprising, but calving events which are limited to the passive sectors of the ice shelves will have very limited impact on grounding line flux, or for that matter, anything that happens over these passive regions, anything that happens to the structural integrity will have very, very limited consequences for flux across the grounding lines. This is in the paper by Ronja Rees. There's also a more recent paper by Tom Mitchell in the cryosphere discussing this for the Larsen C ice shelf. Now, numerically, what this means is that we need to get the, I'm not getting the second video here going, but it sort of does the same, just zooms in. We need to get the dynamics of the grounding line correct. And it seems to be almost impossible to do that without resolving the grounding line sufficiently well in numerical models. And one way of doing that is to use local mesh refinement and then unrefine as soon as the grounding line has migrated through a particular part of the computational domain. Oh, now it starts, okay. So here you can see a large-scale simulation. This is ongoing work by Sebastian Rosia. He's looking at potential tipping points within the Greenland catchment area. And you can see here how the grounding line is retreating. And he has here in this figure down here to the left, flip this around. So here the grounding line is retreating the other way around, but it's the same area. And you can see how the grounding line is being highly resolved as it retreats. And this seems to be the only way of getting this buttressing estimates sufficiently accurately well described. Now, I am sort of going towards the end of the talk. I'm just going to advertise 2 papers that came out recently, which will show what I believe is going to be one of our challenges or opportunities, and that's to make use of all the new data that we're getting, all the remote sensing data, all the observations, and somehow combine this with or assimilate into our models and somehow extract from this interesting information about glacial dynamics and hopefully to improve the modeling capabilities. So this is a paper by Jan de Wit that came out earlier this year. Now, glaciers, they may evolve slowly compared to many other natural systems, but by now the observational record is starting to be sufficiently long and good enough for us to tackle some of the biggest unknowns in glacial mechanics. So, for example, here, look at this. This is Pine Island Glacier. And you can see here the changes in both velocities, delta U, and ice thickness, delta H, from 2016 and 1996. So we have these maps, highly resolved maps of ice shelf thinning, of ice flow, ice sheet thinning, and ice flow changes. And from this, you can calculate, for example, well, you can do many things, but one of the things you can do is to calculate the optimal value of M in Werdner sliding law. So there's a relationship between changes in the surface elevation and changes in the surface velocities. And in the linear theory, this can be calculated analytically. I did that some time ago. And you get an equation of this form where M is the stress exponent in Werdner sliding law, and F1 and F2 are some complicated functions. But what this means is we can now, knowing delta U and delta S, we can simply solve for M. Now, Jan did this actually better than this. He used this sort of as an initial guess and combined this with a numerical model. So he was not limited to assuming that this equation holds, although it turns out it holds pretty well. But this gives us a spatial distribution of the stress exponent in Werdner sliding law. I think this is absolutely fantastic. Now, there are other groups that have been doing similar work, and I think there will be more work of this type being done in the future. But this to me is so significant because we're finally addressing these things, and I can really understand how we arrive at this map for the stress exponent, and it's just a wonderful way of learning more about glacial mechanics and the control of glacial flow. Here's another thing. Remember this video? I had that earlier during the talk. So maybe some of you spotted that when we change, we're changing here the rate factor A, once we get close to the tipping points or the locations where the grounding line sort of jumps over the retrograde slope, it appears that the behavior of the system sort of slows down a bit. And you can see that here on the left-hand side panel here. So here you're looking at the rate factor, which is exactly what we see down there. But you also see on top of this, the grounding line position. And you see that every time that the rate factor is changed, the grounding line position changes. But the response time seems to be a function of the position of the grounding line. And the response time seems to be increasing as we get close to the tipping point. Now, there's a theory behind this. You can actually plot the response time. We can estimate the response time from the curvature. And you can plot this against the ice rate factor, and you get nice straight lines. And there's a general theory behind this. And this allows you to nail down exactly for what value of the ice rate factor you cross the tipping point. So, Sebastian Rocha just published this paper where he did this same kind of analysis for Pine Island Glacier and discovered using this technique that, at least in the model, Pine Island Glacier possesses at least 3 distinct tipping points. And again, I find this absolutely amazing. This has been one of the biggest questions in our field, stability of the West Antarctic ice sheet. And there have been all these papers and all these discussions. Now we actually have a methodology to really nail this down. I find this very, very convincing. Currently, the grounding line of Pine Island Glacier may well be stable, but if you perturb it sufficiently, it will actually undergo an irreversible retreat. So I think I'm just on time, so this will get to the summary and outlook. So my first message to you guys was really, and this was something that I learned the hard way, you know, some problems are actually simple. We don't have to jump at the equations. Sometimes we can figure out things like the steady state length of glaciers by simply looking at basic mass balance considerations. The steady state length of glaciers, where we can ignore the surface elevation mass balance feedback, is given only by surface mass balance considerations alone. And the steady state length of a glacier is independent of any parts of glacial mechanics, as long as this assumption about the surface mass balance elevation feedback being small is valid. It also follows that mass balance is not dependent on climate, because the mass balance of the glacier always evolves towards zero when the glacier reaches a steady state. So when we move from one steady state to another, we're just moving from one situation where the mass balance is zero to another situation where the mass balance again is zero. For the Antarctic ice sheet, we have this very, very different situation. It's all about the flux across the grounding line, and the position of the grounding line and the dynamics of the grounding line are inherently related to glacial mechanics. And while the one-dimensional case, I would say, is now pretty well understood, and we all agree that in one-dimensional case, grounding lines on retrograde slopes are unstable. The more general situation where we have confined ice shelves is much more, much richer, much more surprising. And currently, at least, and that may continue to be the case, there is no way of estimating whether a grounding line is stable or not for a given situation. And one of the reasons for that is that these grounding lines are all so heavily buttressed. This buttressing number, which is equal to 1 when ice shelf is unbuttressed, this buttressing number is more like 0.2, 0.3, or even negative for most grounding lines for the across the Antarctic ice sheet. Now, these are really exciting times. I really feel that it's just within this year, and I can see it happening over the next two, 3 years, we will make a tremendous amount of progress. And that is related to improved modeling capabilities. It is related to many things, but to me, it has a lot to do with great improved modeling capabilities and our sort of confidence that the models are actually robustly describing some things like tricky things like the grounding line migration. But it also has a lot to do with just a vastly better data situation. Glaciology today is a data-rich science. And we are in a position now where we can start to address things like, you know, what is a sliding law? Or we can at least eliminate various sliding laws that we previously had to sort of assume were still in the play. But one of the challenges that I think we as a community have is to establish the predictive capabilities of our models. And I ask, you know, how many successful predictions have we really made? And the way forward here, I believe, is to use the observational record, which now allows for back testing or post predictions, opposite of our prediction. So we can now back test our models against highly resolved spatial and temporal historical variations of glacier behavior. And we should really take a full advantage of this. Now, just to mention that there are papers here that I didn't cite, which I maybe should have cited. The issue with the sliding law that has been looked at in other papers, Ian Jockin and the French, the Grenoble group has looked at this in a number of papers, buttressing the idea that ice shelves affect the stability regime of grounding lines was already mentioned by Dan Goldberg, and there have been papers by Marina Hasselhoff and Olga and Sam Perla and Sue looking at this in more detail. And finally, I have to mention that the work that I'm doing is supported by EU, work there as a part of the TIPAX project, and furthermore as a part of the International Thwaites Glacier Collaboration and the EU project Protect. So thank you.
Awesome. Thank you a lot, Hilmar. Would you have the slide for the seminar of next week?
Yeah, so next
awesome.
week, Mark Carey, Professor of History and Environmental Studies, the University of Oregon, will be giving a talk about the inequality of ice loss, perspectives from a social scientist.
Awesome. Thank you a lot. Really exciting results. Really cool. And there's been a bit of discussion during the talk in the chat with a few questions and even answers. Don't know if those who asked the questions are still there and would like to ask them. I think I see. So Alison had a question, but then had to leave. Maybe I can read it for you if you don't find it. Or maybe you see it, Hilmar.
Yeah, very good. Sorry, I was just going through the chat. Yeah, shame I couldn't see the chat while I was talking. I just couldn't see it. I didn't know how to see it. So I now realize I could have just clicked on it. But yeah, are there any particular questions?
Yeah, I think there was one from Alison. So she had to leave, but then she'll catch up the records. And she was asking, is confined versus unconfined a clear cut, or is there like a fuzzy area between the two types of ice shelves, depending on length, viscosity, or thickness?
I think there will be a general sort of transition. You can have lightly confined ice shelves, and you could have a confined ice shelf where, you know, with time, due to damage and other processes, the margins of the ice shelf break up, and then that ice shelf, which previously was confined, sort of slowly becomes an unconfined ice shelf. Emily Hill did a study on Petermann Glacier where we discovered that although Petermann Glacier has a fairly large ice shelf for Greenland, a fairly large ice shelf, it was effectively unconfined because it was so broken up along the margins. So yeah, so you will have a spectrum. However, if you look at the grounding lines today of the Antarctic ice sheet, most of them are definitely in the heavily buttressed regime.
Great, thank you a lot. I'll just scroll up to see a few more questions.
Shall I stop sharing, or?
Yeah, as you want. Maybe you still want to show them some things, or maybe to answer some questions as you want. Yes, Frank Patin has a question. Frank, do you want to ask it directly, or should I read it? Just wait a few seconds.
Hi, Hilmar.
Great.
Thanks a lot. It's a great talk. Just on your last remark that most of the ice shelves are heavily buttressed, do you consider Thwaites and Pine Island also as heavily buttressed at present?
Yeah, so that may have changed. And I have to say, with the study, well, I don't have it, but we did look into that, at least in that study. But in this particular study, I think the resolution which we used, we could improve the methodology quite a bit if we were to redo this. But at this time, we were sort of limited to having like 20 by 20 kilometer squares. And we were doing this for the whole of the Antarctic ice sheet. So when you get down to ice shelves like Pine Island Glacier, which aren't really that big, then 20 by 20 kilometer resolution is quite poor. So I think there might be an argument maybe for more of a high resolution sort of bespoke studies of this, and also to use a slightly different methodology. It's improved a little bit since we did this. So Frank, I don't know. I would have to look at the paper and see what the value value was. This actually, now you mention this, Jan, if I don't know if Jan is here, but I think Jan looked at this in his study. Where is that study? It's this study, yeah. So Jan did look into this in his study because he was looking at the drivers of change for Pine Glacier, and so he had to look at how heavily buttressed the ground line was, and I can't remember exactly what the conclusion was there. But yeah, it may have changed because the margin of Pine Glacier have been breaking up for the last years. So Jonathan is asking, if you don't know with sufficient accuracy the bedrock topography, how can you get the ground line dynamics right? Well, this is a very good question. So although the stability regime is not determined by bed slope alone, it definitely has an impact on the grounding line migration. And it is very important to know the bathymetry, especially in that critical area around the grounding line. And this is just something that ice sheet models have to try to quantify. And that can be done in an ice sheet model. You always have the luxury of changing things in any way you want, and you can figure out how sensitive your results are to various model assumptions. I think, didn't Sainan Sun do this some years ago? Did a modeling study of, I think, Pine Island and Thwaites, and used various synthetic bed geometries. So there are ways of dealing with this in that sense.
Yeah, that's right. But can I expand on the question a little bit? I mean, because we don't know the bathymetry and the bedrock topography close to the grounding line for, quite a lot of big glaciers in Antarctica, do you think that in effect you're going to have to parameterize some of the grounding line dynamics?
Well, I do feel that it's the job of an ice sheet model to calculate, from first principles, the grounding line dynamics. So I would not want to parameterize them. I think the model should be able to do that. And things
but if you don't know a critical boundary condition, you don't really have any other choice, do you?
So you're referring to the bathymetry as a boundary condition, yeah?
Or yeah.
So one way of dealing with this is to take the bedrock that we know and the uncertainties that are provided in the data sets and generate various synthetic bed geometries where you create new beds which have same spatial correlations as the data set suggests. And that's sort of like changing the bed geometry a little bit in a sort of clever way, and that's one way of doing it. So that can be addressed. Maybe the models don't do enough of that. And further down the line, I mean, Matthew is now inverting for ice thicknesses using the mass balance equation, not the mass conservation equation. So which is then independent from the momentum equations, but maybe in the future, it might not be a bad idea. I think Matthew, you did that and then concluded it wasn't such a good idea. So you can maybe explain this to me. But it might be good to just throw in all these uncertainties into a model, and it should be able to come up with the best estimate for both A and C and the bedrock and the associated uncertainties in these estimates, and then we can, through using ensembles, calculate the resulting uncertainty in our predictions. By the way, there is a paper submitted by Emily Hill, which does exactly that, but not for everything, but for most model parameters, where we use uncertainty quantification to come up with uncertainty in our estimates of changes in ice volume or flotation. And that could be expanded. That same methodology could be expanded to look at the impact of uncertainty in bedrock geometry on our predictions. Yeah.
Great, thank you a lot. I think I don't see any new questions. Just checking Facebook also, because we're live on Facebook. I don't see any question there. So yeah, thanks a lot again, Hilmar, for that awesome talk. And if there are no new questions, then I think we can close the seminar there. Yeah, a lot of thanks from everyone, of course.
Yeah, well, thank you guys. Thank you guys for organizing this. It's been a very, very nice thing to have. So again, thanks to you.
And just thank you, Hilmar, and thank you everyone for joining again. And so, yeah, let's just see you all again next week. Yeah, have a nice evening or day or wherever you are. Thank you a lot, everyone.
Goodbye.
Goodbye. See you.